In this video, we're going to look at the inverse of a matrix. So let's take a 2 by 2 matrix A, 2 rows, 2 columns, and let's label its elements A, B, C, D. The determinant of A, which we write in symbols, just det A for determinant of A, is a number that comes from this matrix. We calculate it as AD minus BC. And this number, this determinant of A, leads us to a formula for A inverse. A inverse is 1 over the determinant of A times the following matrix. We're going to swap the entries on the main diagonal of our matrix A, so that A and the D change places there, and the off diagonal elements here are going to change sign. So this gives us a formula for A inverse, and that works whenever the determinant of A is non-zero. If the determinant of A happens to equal 0, then A inverse does not exist. We are going to find C inverse, and for part A, let's say our matrix C looks like 2, -11, -1, 4. So first thing we should do is calculate the determinant of this matrix. So we're going to go A times D, 2 times 4, minus the product of the off-diagonal elements, so minus -11 times -1. And if we work that out, we've got 8 minus 11, so -3. All right, because this determinant is non-zero, it means the inverse matrix does exist. We can take a look back at our formula here. We're going to go 1 over the determinant, so 1 over -3. And we're going to multiply that by the following matrix. We're going to go back to our original matrix here, and we're going to swap the elements on that main diagonal. So the 2 and the 4 change places, and the off-diagonal entries are going to change sign. So they'll now become a +11 and a +1. So that is our inverse matrix. If we think back to our previous video on operations that we can do on matrices, remember that if you have a number multiplied by a matrix, what we're really doing is just multiplying each element of that matrix by the number. So we could rewrite this as multiplying through by -1/3 and just make it -4/3, -11/3, -1/3, -2/3. So both answers here are good, just two different ways of writing down the inverse matrix. For part B, let's say our matrix C looks like 2, 3, 4, 6. So first thing we'll do is calculate the determinant of C. We're going to multiply the elements on the main diagonal, so 2 times 6, and we're going to subtract off the product of the other two entries, so -3 times 4. So that gives us 12 minus 12, which is 0. Determinant of this matrix here is 0, and that tells us that the inverse matrix does not exist. Now we're going to look at another method for finding the inverse matrix. And this method will be particularly useful for larger matrices, so for 3 by 3 matrices or 4 by 4, etc. So remember, we're always finding the inverse of square matrices. We saw a nice formula for how to find the inverse for a 2 by 2 matrix. But for larger matrices, unfortunately, there's not a quick formula that we can use. So we need a more general method. Well, let's look at the idea of legal row operations. Operations that we can perform on a matrix. We can multiply a row of the matrix by a non-zero constant. We can replace a certain row of the matrix, let's say row I, with itself plus a constant times another row. So in general, we could say we can replace row I with row I plus k times row j. If we want to imagine this a little bit more concretely, we could do something like replace row 2 with itself, and we could have, say, minus 3 times the first row. So you can always replace a row with itself plus or minus a multiple of any other row of the matrix. And last thing we can do, we can switch 2 rows of the matrix. So the plan here for a more general method that finds the inverse matrix, what we're going to do is we're going to write down our matrix A, and beside it, we're going to write down the identity matrix. And we're going to do some row operations. And eventually, as the left side of this matrix here turns into the identity matrix, the right side will be turning into A inverse. So this gives us a general method for finding the inverse for larger matrices. So for our first example of using these row operations, let's take a matrix that we've already worked with. So we used the matrix C, which looked like 2, -11, -1, 4. We used that a few minutes ago and found the inverse. So let's try finding the inverse now using the legal row operation method, and we'll make sure that we can come out with the same answer. So the problem here, just to find C inverse, this time, instead of using our formula, let's use row operations. So first thing we'll do is we'll copy down our matrix C, then we'll draw a vertical bar here, and on the right side we'll write down the identity matrix of the same size. So copying down C, drawing our vertical bar, and over on the right side we'll write the 2 by 2 identity matrix. Remember, the identity matrix has 1s along the main diagonal, 0s everywhere else. Now, what we want to do here is we want to do a sequence of row operations so that this left side here turns into the identity matrix. So first thing we want to do is we want to get a 1 in the top left corner. All right, well, let's take row 1 and divide it by 2. We're allowed to multiply a row by a non-zero constant, so that includes dividing a row by a number. Okay, let's take row 1, divide through by 2. So we're going to have 1 minus 11 halves, and whatever we do the left side, we have to do the right side as well. So we'll have a half and 0. And bottom row here will just stay the same, so we'll recopy that. All right, so we've now got a nice 1. Now that we've got a 1 there, we should clean up the rest of that first column. So what we would really like is to get a 0 down in the bottom left-hand corner. Now, the way we're going to do that is we're going to take this row, row 2, and we're allowed to add on a multiple of any other row. So when you've already got your 1 circled here, it's particularly easy to figure out how to make this 0. We're going to take row 2 and just adding on row 1 will give us a 0, because -1 plus 1 is going to give us 0. So adding row 2 plus row 1, we get 0. And we may have to do some other calculations just underneath here when we're dealing with these fractions. So we'll have to add 4 plus negative 11 halves. Let's see what that gives us. Well, that's going to be 8 halves minus 11 halves will be negative 3 halves. All right, so that's what we're getting down here. Continuing to add row 2 and row 1, we'll get a half and 1. And our top row has not changed, so we'll just recopy that. So this two-step procedure that we just did, that cleaned up the first column. We're going to see this pattern over and over again of getting a 1 in the position where we want a 1, and then cleaning up the rest of that column. So now that we've dealt with that first column, we're going to move down into the right. And this minus 3 halves here now has to become a 1. Remember, we're trying to make the identity matrix on the left side. So we're trying to get a matrix that looks something like this. Well, to make this minus 3 halves a 1, what we want to do is take this row and just multiply by something that's going to give us a 1 here. So let's multiply by the reciprocal of this number. We'll multiply through by negative 2/3, and that will give us a 1 in this position. So I get 0 and 1, and we may have to do some calculation underneath just to figure out what our numbers are. So half is going to get multiplied by negative 2/3. Those 2's are going to cancel, and we'll have a minus 1/3 there. And as we continue to multiply this row through by negative 2/3, we'll get a negative 2/3 there. All right, so let's recopy this top row. That will not be changing at this point. And we've now got a nice 1 in that bottom right-hand corner. Okay, well, last thing that we need to do is, now that we've got a 1 in this second column, we need to get 0s in the rest of that column. So in other words, we now need to fix this minus 11 halves. Well, to get rid of the minus 11 halves, we're in row 1, and what we need to do is add on positive 11 halves times row 2. So to get rid of a minus 11 halves, add on positive 11 halves of the row that contains the 1 in it. All right, so let's see if we can do that. Row 1 plus 11 halves row 2 is going to give us 1 and 0. And then we can do some calculations underneath. So taking row 1 plus 11 halves row 2 is going to give us half plus 11 halves times minus 1/3. Okay, maybe let's turn this into sixths. So we've got 3/6 minus 11 sixths gives us minus 8/6, or minus 4/3 if we reduce that. All right, and then for the very last element in this row here, remember we're doing row 1 plus 11 halves of row 2. So we're getting 0 plus 11 halves times minus 2/3. And if we just cancel the 2's there, that's going to give us minus 11/3. And our bottom row is not going to be changing. Okay, so after a fair bit of arithmetic, we have now produced the identity matrix on the left, and on the right, what we've come up with is our inverse matrix. So as we've gone through and undone the C on the left, we have come up with the matrix that undoes C. In other words, we've produced the inverse matrix on the right. So, and we can check that this inverse matrix agrees with the one that we found from our formula a little bit earlier in this video.